Since the time of John Dalton, scientists assumed that all atoms of a given element had the same mass. Now, the discovery of isotopes required development of a method to represent different nuclides or isotopes of the same element. We will use symbols that contain the relevant information about that isotope, and so it's helpful to define some of those symbols. And most of the time, we will see it represented like this, where X is the elemental symbol. Now, this elemental symbol is the 1 or 2 letter symbol. To identify the type of atom. And it's generally found on the periodic table. So you'll get this from the periodic table. Okay. We also have a mass number. A mass number is represented with an A, and this is the total number of nucleons, which all that really means is it's the protons and the neutrons. So that number is the protons plus the neutrons. That's just the stuff in the nucleus. That's all that means. And then we have the atomic number. And this is the number of protons in the nucleus. Okay. And that really determines the identity of the element. So the number of protons determines the identity of the element. And so if we were to look at a periodic table, for example, if we were to see gold, 79 there, that is the atomic number, or as we represent it as Z. Here in silver, it's 47. So on the periodic table that I'll give you, you will see that number in the top left corner. And so that's how we can tell the number of protons. And what that really means is that every silver is going to have 47 protons, and every gold is going to have 79 protons. So, but what we do know is that gold can have a different mass number because there are different isotopes. Okay, so let's look at that a little bit in more detail. So if we remember that these are set up this way, these symbols of isotopes, we have 2 here for uranium. Notice that the atomic number on both is the same. We have 92 for uranium here and 92 here. But notice that the mass numbers here are different. And that's because there's a different number of neutrons. To figure out the number of neutrons, all you have to do is take the mass number and subtract the number of protons. So to determine the number of neutrons, all you have to do is take the mass number, which is the bigger number. If you forget what the mass number is, it's just going to be the bigger number, minus the number of protons. You will never get a negative number here. You're never going to have a negative neutron. So when we do this, it's always going to be that bigger number, that mass number, minus the number of protons. So let's look at an example where we have to calculate the number of protons, electrons, and neutrons in an atom. And we're actually going to look at 3. So when we look at this and we see a number that is written after the element name, so we've got bromine 79 here. That means that this number here, right, is the mass number. It's just a different way to write that, the isotopes basically. And what you have to do then is you have to go to your periodic table and you have to find bromine. So go to your periodic table right now, and when you look, bromine will be the 35th element, and that 35 is the atomic number. So if this was written in that XAZ format, if bromine 79 was written that way, it would be, right, 79, 35 bromine. That's how we would write it. This is just a synonym for this. But when it's written this way, you have to look at the periodic table to figure out the number of protons here. So this question says, how many protons, neutrons, and electrons are present in an atom of the following? So we have bromine 79. Well, that atomic number is going to tell us immediately what the protons are. The protons are 35, right? That just matches the atomic number. The atomic number tells us the number of protons. There is no charge on bromine, and so that means the electrons have to equal the number of protons. So the protons here are 35, the electrons are 35 because bromine doesn't have a charge, okay? Then, now we have to figure out the number of neutrons. To figure out the number of neutrons, what we're going to do is we are going to take that mass number, which is 79, and subtract the atomic number, which is 35. That gives us 44. And that's our number of neutrons. So there's our protons, electrons, and neutrons. Now, at this stage in the screencast, you may want to pause and try B or C on your own. That's a really great way to use this as a tool to study. If you don't, that's okay. I'm going to work through these as well. So if we look at bromine 81, it's important to understand that bromine 79 and 81, these are isotopes. We've got the same number of protons, but we should expect a different number of neutrons. So the protons here are going to be the same. They're 35. The electrons are also going to be the same. They're 35. And so now we have to calculate the number of neutrons. And so for the number of neutrons, we're going to take 81. That's the mass number for this isotope. We're going to subtract 35, and that will give us 46. And so again, we can see that these are isotopes because they have the same number of protons, but a different number of neutrons here. Let's look at iron. So again, great time to pause the screencast if you want, and work this on your own. So when I see iron 56 here, and I'm trying to figure out the number of protons, electrons, and neutrons, the first thing I need to do when I have this particular form is I need to go to my periodic table. So I go to my periodic table and I look for iron. Iron is in the middle of the periodic table. It's the 26th element. And so you'll see that there. So iron has a 26. So that 26 tells me the number of protons. And because there's no charge on iron, the number of electrons are the same. Because protons are positive and electrons are negative. If there's no charge here associated with iron, if there's no plus or negative, then these two should match because the charges cancel out to give an overall charge of 0. So now let's figure out our neutrons. We would take 56 and subtract 26, and that gives us 30. So that's our number of neutrons. So this whole time I've talked about these atoms not having a charge, right? And I've said, okay, hey, look, the electrons are going to be the same because they don't have a charge. We aren't always going to run into that. Sometimes we are going to have these atoms and they're charged. So what I want to do now is take a little bit of time and talk a little bit more about the electron and what we see with that. So I want to review a little bit from the previous screencast. So on the previous screencast, we talked about the Bohr atom, right? And we said, hey, look, when we talk about this atom, we have a nucleus here with the protons and the neutrons, and the electrons are around it outside. Now, this is a picture of Niels Bohr. He was really interested in electrons. So Niels Bohr studied electrons, and particularly hydrogen, and basically Niels Bohr hypothesized that electrons are outside the nucleus, right, in specific energy levels. And the problem, well, there are several problems here with this that he ran into. One of the problems that he ran into was the exact position of an electron is really difficult to determine because they're in constant motion. So electrons are in constant motion. And the exact position of an electron is very hard to determine. Okay. So instead, when we talk about electrons and where they are, we don't talk about their definite position. We say, hey, the electron will probably be here. So we talk a lot about probabilities. Now, when we talk about these electrons, one of the things that we know is that electrons exist only at distinct energy levels around the nucleus, right? These are sometimes called shells, right? So these are energy levels or shells. And what we know here is that the energy level here, the lowest one, is the closest to the nucleus, right? And it's the lowest in energy, right? And the one that's the farthest away from the nucleus is higher in energy. So basically from this, what I want you to get right, is that you have electrons that are close to the nucleus. They're really low in energy. You have electrons that are far away from the nucleus. These are high in energy. They're more likely to go and bond, right? And they're the ones that we're interested in because we in this class are interested in chemical bonds, okay? Now, so we are most interested in the electrons that are in bonding in this class. And those are called valence electrons. And they're the ones that are the farthest away from the nucleus. So when we talk about this and these valence electrons, they're a lot of times referred to as being in the valence shell. And this is just the outermost shell of any atom. Okay? Now, when we say shell, that can also be known as energy level. Okay? So these are the electrons that are the farthest away from the nucleus. And that should have been written right here with the valence electron. Sorry, I wrote that a little bit up there, okay? And the big thing for us, right, these are the outermost ones, the ones that are farthest away, is these are the ones that play a role in bonding. These are the ones that form bonds, okay? Now, so we have these valence electrons. They're the outermost shell, right? It's important to know that we also have core electrons, right? And these are all of the other electrons that are located in the inner shells. So core electrons are just all the other electrons located in the inner shells. They are not involved in bonding. Okay? So really good example of this is, for example, silicon here. So if we look at silicon, right, and we go to our friendly periodic table, we're going to see that silicon is the 14th element, right? So silicon has 14 electrons, and they're arranged, so here's the nucleus, right? And they're arranged in these levels, that Bohr described around the nucleus, where we have 4 in the outermost shell. 1, 2, 3, 4. Those 4 are the valence electrons. So silicon here has 4 valence electrons. So out of the 14 total electrons, only 4 valence electrons are involved in bonding. We can also figure out how many core electrons it has by taking 14 and subtracting 4. And so now we know we have 10 core electrons. Now, if I don't have this image to look at, how would I know how many valence electrons that silicon has? Well, the periodic table helps us out. So we can look at the periodic table and it can tell us how many valence electrons our main group elements have. So let's talk a little bit about periodic table lingo for just a second. And in one of our screencasts in this module will be dedicated just to the periodic table, but I know we're not there yet. So when we talk about the periodic table at this stage, it's important to know that we have groups, and groups are these columns here, and they can tell us the number of valence electrons for the main group elements. Periods are the energy levels, and they are the horizontal lines. So for this screencast, we're really interested in the groups. When we talk about the main group elements, they're group 1 and 2, and we're going to see there's 1 valence electron in group 1 and 2 valence electrons in group 2. We're going to skip over this middle part here. These are the transition metals. They're not what we call the main groups. To come over here to this, we'll see there's 3 valence electrons in group 3, 4 here, 5, 6, 7, and 8. Now, older periodic tables will have 1, 2, 3, 4, 5, 6, 7, and 8. But a lot of times they'll have a Roman numeral after it or A's and B's, okay? More modern periodic tables will still have 1 and 2 here, but instead of 3, 4, 5, 6, 7, and 8, they'll have 13, 14, 15, 16, 17, and 18. So to figure out the number of valence electrons, all you need to do is drop the 1 here, and that will tell you 3, 4, 5, 6, 7, and 8. And the periodic table that I give you to use during the test and in class will be this type. It's the more modern one. So do get used to that. So let's do an example. Okay. So let's say I have carbon, right? And I'm asked to give the total number of electrons, the valence electrons, and the core electrons. Okay. Well, when I go over and look at carbon on my periodic table, right? It has 6 as its number of protons. There's no charge on this carbon. And so because there's no charge on this carbon, I know that the number of protons and the number of electrons have to equal each other. So we have 6 total electrons here, okay? Because this is going to match that atomic number. I look up here and I see that carbon is in group 14. I'm going to drop this one so that I know that it's got 4 valence electrons. So carbon has 4 valence electrons. And so now to figure out the number of core electrons, I just take the total electrons, subtract the valence electrons, and that will give me the core electrons. So if we go to do this, we take our total electrons, which is 6, we subtract our valence electrons, and that gives us 2 core electrons. Now, this brings us to the octet rule, okay? And when we talk about the octet rule here, elements that are in group 18 have 8 electrons, right? With one exception, except helium that has 2. Now, these elements are extremely stable. And because they're extremely stable, they're incredibly unreactive. Now, atoms of elements in other groups are more reactive because through the process of going through these reactions, they're trying to achieve this configuration of 8 valence electrons. Okay, so atoms of other elements are trying to get 8 valence electrons in their outermost shell to be stable. Okay, and this is the basis for the octet rule, right? Which just states that elements usually react to get 8 valence electrons. Okay, now to get those 8 electrons in the outer shell, elements generally give away electrons or take electrons and through this process form ions. So, right? So atoms can lose or gain electrons, and when they do this, they become ions. So we've got 2 different types of ions that we're going to focus on. One are cations, right? And these lose 1 or more electrons to become positive. And on the periodic table, all of your metals, right, are going to be cations. Okay, they're going to lose the electrons. We're going to talk more about the periodic table in the next screencast, but the metals are found right here. Okay, then anions, these gain electrons to become negative. Okay, and these are mostly your non-metals. Now, why is this important for cosmetics? Okay, so a lot of this is background chemistry. We have to build a foundation before we can apply it to cosmetics. But here, this idea of cations and anions is quite important for cosmetics because many of our body surfaces carry a charge. Right? Specifically, cationic materials are attracted to body surfaces, right? Which is particularly great if you want to leave a layer on the skin. So think about lotion. You'll want to leave a layer of moisturization on the skin. It would be really nice if it was charged with a positive charge because it would stick to the skin better. And so we're going to refer back to these ions as we talk about our cosmetics later in the class. But it's always nice to kind of think about looking ahead and why ions are important. So I want us to visualize this a little bit. Really quickly, right? We have a chlorine atom. A chlorine atom will gain 1 electron. And when it does this, right, the electrons go from 17 to 18. This means that we get a negative charge of 1. Okay, but the number of protons don't change. So look here, protons are 17, protons are 17 here, protons are positive, these electrons are negative. We have 1 more electron than proton. That's where we get that -1 charge. Let's look at sodium. okay? Sodium will lose an electron to have a positive charge. The number of protons are the same. Sodium loses an electron. Now we have 10 electrons. We have one more proton. That's where we get that positive 1 charge. So let's do an example. Okay. How many protons and electrons are present in a single atom of the following? So when we look at the charges here, right, that -2 charge tells me that we have 2 more electrons than protons. So the electrons are the only things that can change. The protons are going to stay the same. So to figure out the number of protons, I'm going to go and look at the periodic table. I'm going to find oxygen with 8. This tells me it's got 8 protons. -2, it says I've got 2 more electrons than protons. That means I must have 10 electrons. So that would give me a -2 charge. We look here at this +2. When I look at that, I interpret that and I say, hey, look, this means we're going to have 2 more protons than electrons. Electrons are negative, protons are positive. To have a +2 charge, you need 2 additional positive things. We come to our periodic table. We find magnesium. Magnesium is going to tell us the number of protons. It's got 12 is the atomic number. So that means it's got 12 protons. That means it can only have 10 electrons to get that +2 charge. Okay. Now at this stage, you may want to pause your screencast so that you can do iron on your own. It'd be really great, and then check your work. So if you want to do that now, this is great. When we look at that +3, that +3 tells me there's 3 more protons than electrons. So we come over here, we look at iron, which is Fe. We come to the 26 there. We say, hey, look, that means there's 26 protons and only 23 electrons. Okay, so that's 3 more protons than electrons. I want you to notice something. The number of protons here always stays the same as the number on the periodic table, right? The only thing you can change is the number of electrons. If it's negative, there's going to be more electrons than protons. If it's positive, there's going to be more protons than electrons. So that's where you have to take away the electrons. We'll practice this more in class, and of course have more things that you can practice on our study guide.